Hello, today we'll be doing today's daily lead code challenge problem, that is counting bits. And the problem statement given here is you are given an integer n, return an array answer of length n plus 1 such that each I in accordance with inclusive of n. Answer of I is the number of ones in the binary representation of I. So what does the question actually say? So let me just take out the pen and I'll draw it and show it to you. So the n is 2 right here. So what are the numbers which are smaller than 2, which is nothing but 0, 1 and 2 itself. So 2 is inclusive. So let's say if my input is 3, so I'll start from 0 up till n, that is 3, right? So this is what you have to do. And then going at each place, that is I. So let's say this is I. You just have to say how many bits are there in this guy, that is 0. How many bits are there in this? How many bits are there in this? And how do we find the bits? So as we know, the binary representation of 0 is 0, of 1 is 1, of 2 it is 1, 0. So this is what we have to do. And after we are done with that, we just have to count how many zeros are, how many ones are there in this bit. There is 0, there is 1 bit, here also there is 1 bit. So let's understand this with a bigger example. Let's say for 5. So for 5, how many elements do we have? We have 0, we have 1, we have 2, 3, 4, and 5. So let's write the binary representations of all these numbers that we have. So 0 has 0 ones, 1 has how many? The binary representation is 1. The binary representation of 2 is 1 0. The binary representation of 3 is 1 1. Binary representation of this will be 1 0 0. Okay, after that this would be 1 0 1. So we just have to count how many ones are there in this. 0 ones in this, 1 1 in this, also 1 in this. How many? 2 ones we have here. Again we have 1, and here again we have 2. So we just have to return this thing right here and store it in an answer vector or answer array and just return it. So this will be my answer. If you just match it, we have got 0 1 1 1 1 2 1 2. So that is exactly my answer which we had needed, right? So for this we could actually use a built-in library that C++ has. So in this, what we could do is, so just get in the built-in pop count. What this does is, so this library functions just gives us how many bits are there in the ith guy. So this will just give me how many bits are there and just push it back into the answer vector. You could also use an array, not a problem, and you could also use a vector array, so that is also fine. So we just did that. Okay, and return the answer. Okay, sorry, since the return type is vector only, we have to use vector. Okay, so just use a vector and just push all the number of ones that we get, and yeah, this is it. And there is also a follow up, if you see here. So this built-in pop count is actually a log n, it takes log n time, right? So if you go through the implementation of built-in pop count, it takes log n to actually find out. So how can we do it in O of n? So if we go to an better solution, that is of O of n, I'll just remove this. I'll show you. So first of all, we need an answer vector of n plus 1. Why n plus 1? I'll get to that. First, let us understand how we get through this. So I've already written the binary representation of every element here. So, okay, yes. So this is 0, this is 1, this is 2, this is 3. So what is the binary representation? Let's get till 5 only. Okay, let's go till 5. So I'll write it again: 0 1 2 3 4 and 5. So how many bits are there in this? 0. How many bits are there we need? That is 1. 2's binary representation is 1 0. 3 is nothing but 1 1. 4 is nothing but 1 0 0, and 5 is nothing but 101. You must be wondering why I have written 1 1 and here I have written 101. See, this is the number of ones that we have in 5. So don't consider this as the binary representation. It is the number of ones we have. So in 5, as you can see, we have two ones, right? So that is why I've written 1 2 times. So this is what it is stating. So if you observe a pattern, so it is nothing but when we are at an even index, let's take this guy right here, even index, we have to just find the I by 2th element and add 1. So if you did not understand this, I'll just walk through this. So what is the binary representation of 2? That is 1 0, right? So what is I by 2? So I is what? 2 right now. So these are my i's, okay? And what do we have to do? We have to do I by 2, right? So this is what we'll get. So what is the binary representation of 2? 1 0. I by 2 is how much? 2 uh, 2 times 1 is 0, right? 2, sorry. So what do we get from here? We get 1 as the quotient, right? And after that we just have to check if I modulo 2 is 0 or not. So if I modulo 2 is 0, so we add 0 to it, otherwise we add 1 to it. So we will add 0 to it. So the formula that I am talking about is nothing but the observation that at my answer, so let's take a as an answer variable, I by 2 plus I modulo 2. So let me just write again so you'll understand this better. So the formula is, that is, I by 2 plus I modulo 2. And why does this work? Let's get through that. So why will this formula actually work? So the basic thing is, I'll write this once again: 1 2 3 4 5, and let's take 6 also. So what do we have for 1? Since we always know the answer for 1, it is going to be 1, right? So let's just say for now it is 1. We are not going through the formula. Now let's come to 2. So what do we have? I is 2 here. 2 by 2 is how much? It is 1, right? 2 by 2 is 1. So write this 1. And 2 modulo 2 is what? 0. So what do we get the answer as? We get the answer as 1, right? So we have only 1 1. See, the answer is only 1 ones. Fine, let's get through more and you'll understand this better. So 3 by 2 is how much? It is 1 again. Got it? After that I see 3 by 3 by 2. This is the modulus operator, okay, and this is just the quotient one. So the modulus operator says I get a remainder of 1 when I divided by 2, okay. So we get this value as 2. So when you do 3 modulo 2, right, when you do 3 modulo 2, what do we get? We get the remainder as 1, right? We get the remainder as 1. See, the remainder is 1. So this is what I've done. I've just added the remainder right here. And what do we get at 4? 4, at 4 we see 4 by 2 is how much? 4 4 by 2 is nothing but 2 here, right? And what is the binary representation of 2? It was 1. And what is the modulus giving us as? 4 modulo 2 is 0, right? Since we do not get any remainder here, we get it as 0. And this is exactly the binary representation. As you can see, we will have only 1 ones here. Fine. Again, when we go to 5, we will see a of I modulo 2. So what is a of I modulo 2? A of I modulo 2 is nothing but 2, right? This is 2. So 5 divided by 2 is how much? 2 only, because that is the quotient. And a of 2 is how much? That is 1. So write the value of a of 2, that is 1, and add on the value of whatever the modulo is. So 5 modulo 2 will give you how much? It will give you the remainder as 1, right? So we get here 2, the answer. Now coming to 6, we see I by 2. 2 threes are 6. So a of 3. A of 3 is what? A of 3. A of 3 is 2. So write 2 here. This will be 2. And what do we get the remainder as? Since 6 is divisible by 2, I know the remainder will be 0, right? So we get the answer as 2. And as you can see, 6 is having 2 ones. So yeah, this is it for this explanation. Now let's get to the code part, which is very easy. If you see it, this is actually not needed. I'll just uncomment this. And yeah, this is pretty much the code. Since I know the answer of 0 will always be 0, right? 0 needs how many bits? 0 bits, right? So the binary representation is 0 itself. So I start from 1, and the formula which is showed to you, answer of I by 2 plus I modulo 2 is what we are doing here. And at the end of the day, we are just returning the answer, and this is my answer vector of size n plus 1. And why did I actually take n plus 1? See, when I'm storing, let's say my n is equals to 4, right? So if I would have written here just n, right, what would happen? My array of size 0, 1, 2, 3. I could have stored the answer till only 3, since the array is 0 based indexing, right? So if I need 4, how much size do we need? So we need n plus 1 size, that is this guy right here. Got it? So this will be n plus 1, and it is also mentioned in the question as well, I think, that we need a n plus 1 size array. If you just go through the question, it is mentioned. See, length of n plus 1, right? So I'll just run this and submit this. It is working fine. Okay. So if you just submit this code, you'll get an AC. I've already submitted this code, so I'm not submitting this again. Okay. So yeah, this is it for this video. If you did understand the solution.